Okay, let's look at the relations among load, shear, and bending moment. We're going to start, if we can, between the relationship between load and shear. Okay, so we have this beam, and it's got some distributed load over here. Well, we're going to start by cutting a little section off here, and let's look at the free body diagram of that. So we have the shear forces, the moments, and then the section of the distributed load. Well, if we take the sum of the forces in y, what are we going to get? Well, we have this going up, this going down, this going down, so the v minus this portion minus this omega times delta x is equal to 0. Well, obviously, those two are going to cancel, and you can go through and solve for it, that delta v over delta x is equal to minus w. When you take the limits, you have delta v over delta x, the limit as delta x goes to 0 becomes a derivative, dv dx is equal to minus w. So what is this saying? That the slope of the shear curve at any point is the load at that point for a distributed load, or the negative to be fair. Okay, so that means that you can go through and you can integrate this, right? If we want to find out what is the change in the shear curve, you multiply through by dx, you integrate it from one point to another, and so the change in the shear curve from one point to another is equal to the integral of the load curve, or in other words, the area under the load curve, the negative of the area under the load curve. So what does that tell us? It tells us that the slope is a shear of the negative, right? We just said that. And an important thing to notice, this is only valid for when the concentrated load, sorry, it's not valid for when a concentrated load, it's only valid for distributed loads. So when you have a single point, this is a different animal. But that is what that's how, this is the key here, that the slope of the shear is the negative of the load at any point in time. Now let's move on to the relationship between shear and bending moments. So again, let's do the same thing. Let's take the sum of the moments here. So if we're talking at this point, you have this shear times this distance, you have this moment, you have this moment, and you have this force, sorry, that was supposed to go straight down, this force times this small distance. So this what you end up with here, right? This and this are positive. This is going to be in the opposite direction. This is going to be in the opposite direction. This is going to be in the positive direction. So there you go. Again, the moments cancel out. So you have your change in moment or change in x is v minus 1/2 omega delta x. So let's take the limit of that as delta x goes to 0, right? So we have the limit of this equation. Well, if delta x goes to 0, then boom, that goes to 0. And so you have your derivative of your moment at any point is equal to the shear value at that point. So same deal, we can go through and multiply through by dx and integrate it. So your change in your moment from any one place to another is equal to the integral of v dx, which is the area under the shear curve. Okay, so what is this telling us? The slope of the bending moment is equal to the value of the shear. That's nice. Again, only valid for distributed loads, not valid for a single point. And then one other thing to consider with this is the shear is 0 at points where the bending moment is a maximum, right? So when we're trying to find the maximum bending moment, because of this right here, good old calculus says if we're trying to find the maximum value, you set the derivative equal to 0. And so the shear has to be 0 where the bending moment's at a maximum. So let's look here like a little example. We have just a nice constant distributed load over this thing. So what is that? Oh, there we go. So the reactions at the supports are going to be, so this is W times L is the total load. It's going to be in the middle. Since it's evenly distributed, it's going to half at each end. So the reaction at each one of them is going to be half. Okay, so and then we have our shear curve. So this shear curve, you go through and you integrate it, right? So you integrate over there. And then, so you're knowing the change across here is given as that. Now, but specifically, let's think about there. What is V at A? So what is the shear at A? Well, the shear at A has to equal WL over 2. So there's a force here. The shear is going to come down this way, and it's going to be WL over 2. So the shear at any point in time is WL over 2 minus WX, which is this nice straight line. Again, this is true, but to me, this is the more helpful thing. This is a good old-fashioned y equals mx plus b, right? Negative omega x plus b. So let's look at the moment curve. The moment, same deal, you integrate the moment, and integrate the shear to get the moment. Well, we know what the shear is, we just figured it out right here, right? Boom. Here is the shear. And so you go through, you can integrate across here. What is the moment here at 0? It's 0. So it starts at 0. So therefore, you have the moment curve that looks like that. And whoa, try again. And the max of that moment curve is, again, where the shear is equal to 0. So we know the max is going to be right here, and that's the maximum. And you can plug it into your equation, and you end up with the max is WL squared over H. So let's do a couple examples to show this off. We'll do example 7.4 and 7.6.